All right, welcome. Today we are going to unlock the secrets of how things move. Seriously, we're building a whole toolkit, one that'll let you describe, visualize, and even predict motion. We'll start with the basics and work our way up to the really powerful equations physicists use every single day.
So, have you ever wondered how we can predict the exact path of something? From a simple baseball toss to a satellite zipping around the Earth? Well, it all boils down to just a few key rules, what you could call the language of motion. And look, if you want to figure out where something's going, you've got to know how to describe where it is right now and exactly how fast it's moving. Okay, let's jump right in.
Okay, so to get this right, we have to be super precise with our words. In physics, everyday words like distance and speed, they have really specific meanings that might be a little different than how you use them. So let's kick things off with the difference between distance and displacement.
Okay, check this out. Imagine a little particle zipping along this curvy path from point A to point B. The actual full length of that winding journey, that's the distance. In this case, it's 16 meters. But displacement, that's a totally different beast. Displacement is just the straight line shot from where you started to where you finished. It doesn't care about the scenic route you took. So here, it's just 10 meters straight down. It's all about the start and the end point. That's it.
And you know what? This exact same logic works for speed versus velocity. Think about your car's speedometer. It just shows you a number, right? That's your speed. It's what physicists call a scalar, just a magnitude. But it doesn't tell you which way you're going. For that, you need velocity. Velocity is a vector. It has both the speed and the direction. So saying I'm going 100 kilometers an hour is speed. Saying I'm going 100 kilometers an hour east, now that's velocity.
Okay, but life isn't always a straight line at a constant speed, right? Things speed up, they slow down, they turn corners. So what happens when velocity isn't constant? Well, to talk about that, we need to bring in one of the biggest concepts in all of motion physics, acceleration. So what is acceleration? It's simply the rate of change of velocity. It's how fast your velocity is changing. And here's the kicker. Since velocity includes direction, you can actually accelerate without even changing your speed. Think about it. A car going around a corner at a perfectly steady 30 miles an hour. The speed is constant, but because the direction is changing, the velocity is changing. And that means, yes, it is accelerating. That's a really crucial idea to get.
Right. So the big takeaway here is how acceleration and velocity play together. If they're both pointing in the same direction, the object speeds up. Simple enough. But if they're pointing in opposite directions, like you're moving forward but accelerating backward, the object slows down. What we casually call deceleration. And of course, if there's zero acceleration, the velocity just stays the same. The object just cruises along.
Okay, all these concepts, they get so much clearer when we can actually see them. Graphs in physics aren't just boring charts, no way. They're like a storybook of an object's journey. You get the whole history of its motion, all in one single picture. It's pretty cool. So, let's start with a position versus time graph. The key thing to look at here is the steepness of the line, what mathematicians call the slope. That slope is the object's velocity. So if you see a really steep line, that thing is moving fast. A shallow line, it's moving slow. And a totally flat horizontal line, well, that means its position isn't changing, its velocity is zero. It's just sitting there.
Now, the velocity time graph, this one is a real powerhouse. It gives you two amazing pieces of information for the price of one. First, just like before, the slope tells you something. But this time, the slope of a velocity graph is the acceleration. But that's not all. The area under the line, that tells you the total displacement. You can literally calculate the area of the shapes under the graph and figure out exactly how far the object is moved. How cool is that?
And this just shows that relationship perfectly. Let's follow this car's journey. On the left, you see the displacement graph. It's a curve, right? That means its position is changing, but not at a steady rate. Now look to the right. That same exact journey, shown on a velocity time graph, looks like a series of straight lines. Each straight line represents a period of constant acceleration or deceleration. See? It's the same story, just told in two different, but totally connected languages.
Okay, graphs are awesome for visualizing stuff, for sure. But what if we need to make really precise numerical predictions? For that, we need to break out the big guns, the ultimate toolkit. I'm talking about the equations of motion. This is really the mathematical heart of everything we're talking about.
These 4 equations right here, they're going to be your new best friends for solving motion problems. People often call them the SUVAT equations, just as a little mnemonic for the variables involved. They create this incredibly powerful link between our 5 key players: displacement, S, initial velocity, U, final velocity, V, acceleration, A, and time, T. And here's the magic. If you know any 3 of those, you can pretty much always figure out the other 2.
But there's a catch. Like any powerful tool, this toolkit comes with a warning label. These equations only work under 2 very specific conditions. 1, the motion has to be in a straight line. 2, and this is the big one, the acceleration has to be constant. If the acceleration itself is changing, sorry, these equations are out and you need to get into calculus. But for now, let's stick to the world of constant acceleration and see what these things can do.
All right, enough talk. Let's put this toolkit to the test. The only way to really get a feel for these equations is to actually use them. So let's walk through a couple of classic problems together.
Okay, first scenario. Picture a sprinter, coiled and ready in the starting blocks. The gun goes off. We know he starts from a dead stop, we know his final speed, and we know exactly how long it took him to get there. So the question is, what was his average acceleration?
So, how do we tackle this? We use a simple step-by-step process. First, let's just list out everything we know. That phrase, from rest, is a huge clue. It tells us the initial velocity, u, is 0. We know the final velocity, v, is 9.0 meters per second, and the time, t, is 1.5 seconds. The thing we don't know is a, the acceleration. So we look at our 4 equations and ask, which one has u, v, t, and a in it? Ah, there it is. v equals u plus at. We just need to jiggle it around algebraically to solve for a, plug in the numbers we know, and boom, we get an acceleration of 6.0 meters per second squared.
Now, there's a really special kind of constant acceleration that we experience every single day: free fall. If you can ignore air resistance for a moment, every object falling near the Earth, I don't care if it's a feather or a bowling ball, accelerates downwards at the exact same constant rate. We give this special acceleration its own letter, g. It's about 9.81 meters per second squared, but a lot of the time we just round it to 10 to make the math a little easier.
Okay, so let's use that. Imagine you drop a stone. If it falls for exactly 3 seconds before it hits the ground, how far did it actually fall? This is a super classic freefall problem.
We're going to follow the exact same process. First, what do we know? The word dropped is another key clue. It means the initial velocity, u, is 0. We know the time, t, is 3 seconds. And we know the acceleration, a, is just g, which we're calling 10. We're looking for the distance, s. So which equation connects s, u, t, and a? That would be s equals ut plus 1/2 at squared. Since u is 0, that whole first part of the equation just disappears. That makes it easy. It's just 1/2 times 10 times 3 squared. Do the math and you get 45 meters. That's it!
All right, you've seen the method. Let's quickly run through a few more common scenarios you might encounter, just to see how flexible these ideas really are.
Let's start with a couple of problems you could almost imagine in real life. First up, a cyclist. They're going 24 kilometers an hour for 75 minutes. How far do they get? The only little trick here is to make sure your units match. The speed is in hours, so we need to convert 75 minutes into hours, which is 1.25 hours. From there, it's super easy. Distance is just speed times time. That gives us 30 kilometers. Okay, next one is a bit trickier. An airplane flight with 2 parts. To get the average speed for the whole trip, you can't just average the 2 speeds. That's a common mistake. Nope, you have to find the total distance and divide by the total time. So we figure out the time for each part. The first leg is 2 hours, the second is 1.6 hours, for a total of 3.6 hours. The total distance is 2,200 kilometers. Divide those and you get an average speed of about 611 kilometers per hour.
And what's so wild is that these exact same principles work whether you're talking about something impossibly tiny or absolutely massive. Let's look at an electron whipping around a nucleus. We know its mind-boggling speed in the tiny, tiny fraction of a second it takes to do 1 lap. Just by tweaking our basic speed formula for a circle, we can figure out the radius of its orbit, a distance that's almost incomprehensibly small. Now let's go from the smallest thing we can think of to the biggest, our own planet. If you're standing on the equator, you're traveling the entire circumference of the Earth every single day. We can use our simple speed equals distance over time formula and find out that you're moving at an incredible 470 meters per second, right now. Isn't that amazing? From an atom to a planet, the physics doesn't change. So there you have it. From the basic but crucial difference between distance and displacement, to seeing the story of a journey in a graph, all the way to the incredible power of those kinematic equations, you now have the core toolkit to describe and even predict the world in motion. Think about it. The very same rules that govern a falling apple are the foundation for understanding the majestic orbits of planets and galaxies. So what are you going to see differently now? Thanks for joining me for this explainer.